Welcome back. Over the centuries, engineering materials have had a profound influence on the world's great structures. Consider these two structures. At first glance, you might even think you're looking at two photos of the same tower, but nothing could be farther from the truth. On the left is the Campanile, or bell tower, of the Piazza San Marco in Venice, Italy, constructed in several phases between the 9th and the 16th centuries. On the right is the MetLife Tower, one of New York City's earliest skyscrapers, built in 1909. And while the MetLife Tower's form was modeled on the Campanile in San Marco, the two structures couldn't be more different. The Campanile's impressive height, 323 feet, was achieved through the use of massive brick walls, over 12 feet thick. So thick, in fact, that they leave just a 12-foot square area of usable space inside the tower. The MetLife Tower, on the other hand, uses an innovative steel frame to achieve its record-breaking height of 700 feet while providing over 200,000 square feet of interior commercial floor space. The exterior walls of the MetLife Tower are just a thin limestone veneer. The difference between the Campanile of San Marco and the MetLife Tower can be summarized in one word: steel. The unique properties of steel enabled the MetLife Tower's great height and its efficient use of interior space. This is a typical example of the influence of materials on the form, function, and structure of a great building. In many respects, steel is an ideal engineering material. And so I'm starting today's lecture with this particular material because it serves very nicely as a benchmark for comparison with all of the other materials that we'll be talking about later in the lecture. And in comparison with those materials, iron, concrete, wood, stone, and brick, steel really is superior in terms of all three of those principal mechanical properties: strength, ductility, and stiffness that I talked about last lecture. Let's use the stress-strain curve for a typical structural steel to review these properties. The most important mechanical property of any material is strength. It's the largest stress a material can withstand without failing. To be precise, the overall height of the stress-strain curve, as shown here, is called the ultimate strength. For this particular structural steel, the ultimate strength is about 65,000 pounds per square inch, significantly higher than the other materials we'll be comparing steel with shortly. And unlike these other materials, steel has roughly equal strengths in tension and compression, a really vitally important aspect of its performance as a structural material. Of course, many materials are stronger than steel, but none of these would be practical or economical as construction materials. Diamond, for example, is perhaps 50 times stronger than steel. We're not likely to see skyscrapers made of diamonds anytime soon. Next, ductility. It's the capability of a material to undergo large, plastic, that is, permanent deformations before fracturing. It's represented by the width of the stress-strain curve, that is, the strain at which fracture occurs. Ductility is a very good thing. Because a ductile material experiences large plastic deformations before it fails, it's able to absorb a tremendous amount of energy when it's overloaded, for example, in an earthquake. It also gives plenty of advanced warning when a failure is imminent, because those large plastic deformations are quite visible to occupants of the building. Structural steel is very ductile. As the stress-strain curve indicates, steel typically elongates over 25% beyond its original length before fracturing. Indeed, the world's most ductile material, gold, is really only a bit more ductile than steel. The opposite of ductility, by the way, is brittleness. Glass is a great example of a brittle material. And because brittle materials fail suddenly, without warning, they really aren't very desirable as structural materials. Nonetheless, there are many important structural materials like stone, concrete, and cast iron that actually are quite brittle, particularly when they're loaded in tension. And that's why we usually see these materials carrying load in compression in columns and arches, for example. Stiffness, the third of our important material properties, is the material's capacity to resist elastic deformation, represented by the slope of the elastic portion of the stress-strain curve. The slope of a line is defined mathematically as the rise divided by the run. When we calculate this number for a stress-strain curve, we get an important material property called the modulus of elasticity. A stiff material has a high modulus of elasticity. We'll see some really important applications of this property when we discuss columns in Lecture 5. Stiffness is also a good thing. Stiffer materials deform less under a given load, and so they're particularly useful for structural applications where deformation is a concern. Skyscrapers, like the MetLife Tower, for example, are particularly susceptible to lateral sway caused by wind loads. Steel provides the stiffness necessary to control this sort of deformation. While steel exhibits the ideal qualities of strength, ductility, and stiffness, it's not an ideal material in all respects. In fact, steel has several important major limitations as a structural material. First, it's susceptible to corrosion, the long-term deterioration caused by the chemical reaction between iron and oxygen. You probably know this phenomenon as rusting. It also has very poor fire resistance. By the time steel reaches 900 degrees Fahrenheit, it will have lost about 30% of its tensile strength. By 1400 degrees, it will have lost nearly 90% of its strength. That's steel. Now let's examine some of these other common materials, wood, masonry, concrete, and iron, and see how they've been used in great structures through the ages in a manner consistent with their material properties. First, wood. Wood has been used extensively throughout history, including prehistoric times, because it's available in most regions of the world and because it can be worked quite easily with simple tools. Wood is the lightest of the common structural materials, and we can see that very evidently with a very simple demonstration. These two small structural members are exactly the same size. Their dimensions are identical, their lengths are identical, their widths and their thicknesses are identical. So what's their difference in weight? Well, we know the steel is heavier, but how much heavier do you think it is? Twice as heavy? 3 times as heavy? Let's see. When we place this steel bar on our scale, we see that it reads about 0.6 pounds. Now let's try the wood. When I place the wood member, which is identical in size, on the same scale, look carefully, because what you'll see is the scale hardly registers any weight whatsoever. It's less than 1/10 of a pound, and therefore about 1/10 of the density of steel. Now, if we compare typical stress-strain curves for wood and steel, we see that a typical type of wood, oak, is only about 1/4 the strength of structural steel. And since it's only 1/10 the weight of steel, what we can see is that the strength-to-weight ratio, which is a very good measure of structural efficiency, is actually a lot higher than that of steel. And that certainly explains the fact that wood, while we think of it as a sort of a primitive structural material, is actually still very commonly used today. Wood is also much less stiff than steel, as you can see from the shallower slope of oak's stress-strain curve. We can also see it in a very simple demonstration using those same two elements that we just used as the basis for evaluating the weight and density of the material. If I now use each of these two elements as a beam, I can place them in position spanning between the two bricks. And if I place a load on each of these beams at midspan, watch carefully and you'll see that under the action of this load, the beam bends about 1/10 of an inch. That's a pretty good reflection of the stiffness of steel, its capacity for resisting elastic deformation. Now, if I do exactly the same test on the wooden member, which again, remember, has identical dimensions, we find that those flexural deformations, the bending deformations, are in excess of 2 inches, more than 20 times larger than the deformations that we saw in steel. So clearly there is a vast difference between the stiffness of these two materials as well. Now, as we're looking at these stress-strain curves, notice that for clarity, I've cut off most of the right-hand end of the steel stress-strain curve. Recall that the failure strain for steel is about 0.25, 25%. So if I ran the horizontal axis of this graph all the way out to 0.25, the curve for oak would be squashed so tightly against the left-hand side of the graph that you wouldn't even be able to see it. This tells us that wood is a relatively brittle material. Its failure strain is quite small in comparison. Steel is about 25 times more ductile. Like steel, wood has roughly equal strengths in tension and compression, a very desirable quality. And this, in fact, was unique among the materials that were available to ancient and medieval builders. Stone and brick masonry, as well as concrete, all have very low strength and tension, even though they have relatively high strength and compression. Recall that beams and trusses both require materials that are capable of carrying both tension and compression. And so virtually all of the long span beams and trusses that we know of from the ancient and medieval worlds were made of wood. Here are some fine examples of early medieval wooden roof trusses spanning the nave of this beautiful little Romanesque basilica in Florence, Italy, San Miniato al Monte. We'll be looking more closely at this incredible structure in a later lecture. Another important attribute of wood is its natural beauty, which accounts for its continued use in modern buildings like St. Maximilian Kolb Church in Westlake, California, shown here. Wood also has several disadvantages as an engineering material. In addition to its brittleness and low stiffness, which we've already seen, wood is also subject to rot. It's highly flammable, and because it's a natural material, its mechanical properties are much more variable than, say, iron or steel. We've all seen knot holes in wood, and a knot hole represents a point of weakness. That's a significant challenge for structural designers trying to plan for the use of material in engineered systems. Wood is also subject to an interesting phenomenon called creep. It's a tendency to experience long-term increases in deformation, even under a constant level of load. In the beautiful old half-timbered houses that you see all over Europe, we can often see a pronounced sag in the beams that are used as part of the outer walls of these buildings. In comparison, materials like steel and other metals experience no creep at all. That pronounced sag is a clear indicator of this long-term tendency of wood to deform over many years. And finally, it's important to remember that wood is an exhaustible natural resource. Back in the ancient world, timber was in very high demand for shipbuilding and construction and heating and charcoal, which was used for smelting metals. As a result, most of Greece, for example, had been almost completely deforested by the 5th century BC. This was an environmental tragedy, and it really persists even to this day. But it did produce one interesting and positive outcome. The shortage of timber almost certainly contributed to the increased use of masonry construction in ancient Greece, and therefore is part of the reason why we have these more enduring architectural features and architectural wonders that have come down to us from Greece's golden age. Okay, let's move on to the next type of engineering material, stone and brick masonry. It's another family of construction materials dating from prehistoric times and still in wide use today. Back in the ancient world, masonry construction was very heavily influenced by geography. When a civilization developed in a river valley, like Mesopotamia, for example, alluvial deposits provided the raw materials for the manufacture of mud brick. When civilizations developed near rocky outcroppings or mountains, stone was more commonly used as the material for masonry construction. In ancient Egypt, for example, the vast quantities of stone used to build the pyramids were quarried from the rocky borders of the Nile Valley. We have archaeological evidence for mud brick construction at least 10,000 years ago. Here's some example of mud brick construction. Mud bricks are made from clay, usually mixed with straw to improve its strength, and then simply left in the sun to harden. Now, around 3000 BC, builders discovered that they could significantly improve the strength and durability of clay bricks by firing them in a kiln. But firing requires fuel, and wood, as we've seen, was very scarce in many areas of the ancient world, so sun-dried mud bricks continued to be used extensively, and in fact, they're still in use throughout that part of the world today. Mud bricks were used to build monumental ancient structures like this one, the Sumerian ziggurat of Ur, constructed in the 21st century BC in the region of modern-day Iraq. The original step pyramid probably measured about 210 feet by 150 feet. But these dimensions are really speculative because the ziggurat has fallen into ruin on a number of occasions and has been rebuilt in response to the periodic decays of the structure, most recently by Saddam Hussein. Another great mud brick building is the Great Mosque at Jinnah in Mali. It was built in 1907 and remains the largest mud brick structure in the world even today. Those interesting posts projecting from the walls are actually bundles of palm branches that serve as built-in supports for scaffolding, which is used to perform near constant maintenance on the walls. And this phenomenon of mud brick construction, frequent maintenance and frequent reconstruction, as we see at both the Ziggurat of Ur and the Great Mosque in Jeddah, illustrate the greatest limitation of mud brick construction: poor durability. The normal lifespan of a mud brick wall is only about 30 years unless it's intensively maintained. And that's why so few of these great structures in our current course are actually made of mud brick. There just aren't that many of them left. Kiln-fired brick, on the other hand, largely solved this durability problem in regions of the world where it was used. By the Roman era, the mass production of fired brick had been largely perfected and standardized across the empire. Few people realize it, but the Emperor Justinian's extraordinary basilica at Hagia Sophia in Constantinople was made entirely of brick. Okay, let's move on to stone masonry construction, which also began in prehistoric times with a relatively crude technique of stacking uncut stone and then waterproofing the joints with mud. But over time, stone cutting tools and mason skills improved, and technologies for quarrying and transporting these large stones were developed, ultimately resulting in structures of unprecedented size and precision. The Egyptian pyramids, shown here, represent not just extraordinary stone masonry structures, but also an important historical milestone, our earliest evidence of the systematic technological planning and management that we now associate with engineering. Many of these early stone structures were so precisely fabricated that the joints between the stones required no mortar at all. But even where mortar was used, it's very important to recognize that mortar joints aren't capable of carrying any tension. Mortar is not a glue that binds stones or bricks together. Rather, it's really only there to make the masonry more or less watertight and to provide a uniform bedding surface for each successive course of stone or brick so that vertical loads can be transmitted down through those courses without concentrations of stress. So all forms of masonry, stone and brick, have relatively high strength and compression, but essentially no strength and tension, specifically because the mortar joints, when subjected to tension, simply pull apart. An important difference between stone masonry and brick masonry is that large stones can be used as individual structural elements, like beams and columns. And unlike the joints between stones, which have no tensile strength, the stone material itself does in many cases have substantial tensile strength. Certainly not as large as a metallic material like iron or steel, but it does have some strength. And so from antiquity to modern times, we see many examples of stone beams, for example. The massive horizontal stones spanning from column to column at Stonehenge are in fact great examples of stone beams. And although both brick and stone masonry are ancient technologies, they continue to be used as load-bearing structural elements well into the 20th century. For example, the 400-foot tall Nebraska State Capitol, completed in 1932, is a wonderful example of modern stone masonry construction. In fact, stone and brick continue to be used today, though typically as decorative veneers, as we saw in the MetLife Tower, rather than as structural elements. Okay, on to concrete. Currently, the world's most commonly used construction material. It came into widespread use in the Roman era, starting around 300 BC. However, the technology was essentially lost to the Western world after the fall of Rome and only came back into common use in the 18th century. Since then, it has been essential for the design and construction of most great structures. Let's talk about how concrete is actually made. Concrete is a combination of three basic ingredients. We have cement, this fine gray powder. You buy it in sacks at your local hardware store. Let's add that to our mixing bowl. We also have aggregate. It's a granular material, normally a mixture of sand and gravel. Sort of a filler, but it also adds most of the strength that will characterize the completed concrete. And before I actually mix everything together, I need to first pre-mix the dry components so that they're well blended together. And this is really important because of the way concrete actually works as a structural material. When I add water to the mix, To add water carefully to get just the right amount. When we add water to the mix, it blends with the cement, and it actually forms a paste. And that paste will ultimately harden as a result of a complex chemical reaction. What happens to the paste is that it fills in the spaces between the granular aggregate. Between the grains of sand and the pieces of gravel, there are very small open spaces, voids. The cement paste fills those voids, and as a result, gives concrete the capacity to harden into a very solid mass when it's completely cured. And that solid mass is what makes it so effective as a structural material. It really turns it into, effectively, a man-made stone. Okay, so now we have our concrete mix in place. We're going to add it to a form, and this is the way modern concrete construction is normally done. A temporary form is prepared, which contains the concrete while it's still in liquid or semi-liquid form, and that set of forms then is responsible for creating the final form of the concrete structure. When we put the concrete into the mold or temporary formwork, I need to consolidate it. That is, I need to vibrate it a little bit so that it ultimately fills in all the spaces within the formwork. Of course, there's more. In this case, I have the luxury of being able to shake it a little bit in order to get the concrete consolidated and down into all the little voids within our mold. And then once we're done with that process, I use what concrete constructors call a screed. That's just a piece of wood that allows me to strike off the excess material from the top of the mold and consolidate it so that we now have a nice flat surface of concrete on the top of our mold, and our concrete construction exercise is now complete. Now, concrete sets up in a few hours, but it actually takes several weeks to reach its full strength. Fortunately, it would be strong enough so that next lecture, when we talk about columns, we'll be able to use this. And in fact, what will eventually emerge from these forms is a capital of Trajan's column. Stay tuned and see how it turns out. In ancient Roman concrete, the cement was a mixture of lime and a volcanic ash called pozzolana, named after the village of Pozzuoli near Mount Vesuvius, where the material was first obtained. Pozzolana produced a very strong, durable concrete that was even capable of hardening underwater. The aggregates typically were rubble, stone, broken bricks, or pieces of clay tile. You know, when you look at a Roman building like this immense Basilica of Constantine in Trier, Germany, you might think you're looking at brick masonry. In fact, you're looking at a particularly ingenious form of concrete. In modern construction, we use temporary forms, just like I just used in my demonstration, to contain the concrete while it cures. And then when we remove the forms, all that's left that's visible on the outside surface is the hardened concrete. But the Roman system, which was called opus latericium, is fundamentally different, and in some ways it's actually superior to modern methods. In opus latericium, which is illustrated here, bricks, often triangular in shape, were used to form the outer surfaces of the wall, and then the space between those bricks was filled with concrete, which actually provided the wall's structural strength. The brick facing eliminated the need for any temporary formwork, and then it gave the finished wall a much more pleasing finished appearance. By standardizing these sorts of building systems, the Romans were able to design and build an amazing variety of concrete structures all over the empire. The greatest of these was certainly the Pantheon, this incredible monument, not just to Roman engineering, but to Roman expertise in concrete construction. We'll be examining this extraordinary building in Lecture 13 in much more detail. Modern concrete now uses something called Portland cement. It's a manufactured product that's chemically somewhat different from Roman pozzolana, but it works in essentially the same way. The first process for manufacturing modern cement was developed and patented in 1824 by a man named Joseph Aspdin, a British mason. Aspdin called his product Portland cement, not because it was made in Portland, but rather because the cured concrete resembled a popular type of natural building stone that was found on the Isle of Portland. So when you buy a sack of Portland cement today at your local hardware store, you're actually experiencing a nearly 200-year-old marketing campaign that succeeded beyond Joseph Aspden's wildest dreams. Now let's explore the mechanical properties of concrete. Note that unlike the curves for steel and wood, the stress-strain curve for concrete is based on a compression test rather than a tension test. Concrete fails at such a low amount of load and tension, about 500 psi, that the tensile stress-strain curve for the material wouldn't even show up on this graph. It would be so low. But even in compression, concrete isn't nearly as strong as steel. In practice, however, because it's so inexpensive, we can generally get very high compressive strength in a member by simply using a much larger cross-sectional area than we would with steel. Concrete has a very good fire resistance property, and it's reasonably good weather resistance as well. But as you can see from the diagram, it's also quite brittle. Perhaps concrete's most important weakness is its poor tensile strength. In modern times, this limitation has been largely offset by the use of steel reinforcement. To give you some sense of the benefit gained from steel, a typical reinforced concrete beam is more than 10 times stronger in flexure than an unreinforced concrete beam with the same dimensions, and its ductility is more than 50 times greater. Reinforced concrete is so fundamentally different from plain concrete that it's really best to think of reinforced concrete as a different engineering material entirely. Its development is a fascinating story, but understanding it actually requires a few more engineering mechanics concepts that we haven't covered yet, so we'll discuss modern reinforced concrete structures later on in the course. Without question, concrete's greatest advantage over other construction materials is its versatility of form. From the ancient dome of the Pantheon to the concrete spiral of Frank Lloyd Wright's Guggenheim Museum in New York City, concrete allows us to create structures of virtually any shape. As my friend Rick the Concrete Guy says, if you can build the formwork, I can fill it with concrete. On to iron. Iron has been produced by human civilizations for roughly 4,000 years. As a structural material, it's used in two different forms: wrought iron and cast iron. What's the difference? In general terms, wrought iron is made by heating iron ore in a furnace until it's extremely hot, but not hot enough to melt. This process is called smelting, and it produces a lump of hot iron called a bloom, which is then beaten with a hammer or flattened with heavy rollers to remove impurities and increase ductility. The earliest form of wrought iron was probably produced by the ancient Hittites in the 2nd millennium BC. In ancient Greece, builders used small iron connectors to strengthen stonework, but the material was really never available in sufficient quantities for complete structural elements like beams or columns. By the 2nd century AD, though, the Chinese were using wrought iron for suspension bridge chains. Cast iron is created by heating iron ore until it does become liquid, and then pouring it into a mold, very much the same way that I poured concrete into a mold a few minutes ago. The finished product also includes a significant amount of carbon, roughly 2 to 4%, which is the material that actually contributes to both the compressive strength and the brittleness of cast iron. Cast iron was probably developed in China in the 6th century BC, but it didn't really appear in Europe until about the 14th century. In the 14th and 15th centuries, European technology for making iron advanced rapidly in response to the need for improved cannons and other military hardware. By 1779, the Industrial Revolution was in full swing, and the resulting advances in iron-making technology were reflected in this great structure, the world's first all-iron structure, the Iron Bridge at Coalbrookdale, which is in fact the ancestor of many great structures from the Eiffel Tower to modern skyscrapers. Adding both wrought and cast iron to our collection of stress-strain curves, we can see that wrought iron has essentially the same properties as steel. It's relatively strong, not quite as strong as steel, but still quite strong. It's stiff and it is ductile. Cast iron, on the other hand, is quite brittle and relatively weak in tension. For these reasons, we often see 19th century structures made of both cast and wrought iron. Cast iron for the compression members and wrought iron for the tension members. We'll see this sort of tailored use of iron structural components in Lecture 7 when we examine the roof trusses of this building, the oldest all-iron building in the United States, located at Watervliet Arsenal in upstate New York. Iron reigns supreme, as a structural material until 1856, when the development of the Bessemer process made the mass production of high-quality steel possible. Steel is an alloy, a mixture of iron and carbon plus small amounts of other elements like manganese and chromium. In very general terms, steel has more carbon than wrought iron, but less than cast iron, just enough to add strength without compromising ductility. Steel was used initially for railroad rails, but eventually found its way into construction starting around 1870. And when James Eads decided to use steel for the monumental arches of his bridge over the Mississippi River in 1874, it was considered to be a very risky decision. We've come a long way since then, and today steel is the material of choice for the world's longest bridges. Steel's dominance of tall building construction is being challenged today, though, by the new kid on the block, high-strength concrete. In 1998, the concrete Petronas Towers in Kuala Lumpur, Malaysia, surpassed the steel Sears Tower in Chicago to become the world's tallest building, the very first time ever for a concrete structure. Yet this structure still depends heavily on steel reinforcement for its load-carrying capacity. This interplay between steel and concrete exemplifies the critically important role that materials play in the engineering design process. Engineering materials will be with us for every remaining lecture in this course. Next lecture, we'll resume our exploration of the 6 basic types of structural elements with the column. And when we do, we'll see that the material properties of strength and stiffness have a profound influence over this structural member's performance as well. Until then, thank you.